Module 26, Lecture A, Mixtures Covariance. By the end of this lecture, you will be able to fit Gaussian and Bayesian Gaussian mixture models for soft clustering and density modeling. Select mixture complexity using covariance structures, AIC and BIC, and apply covariance and precision estimators for robust or structured covariance analysis. Gaussian mixtures, GMM fitting. A Gaussian mixture model represents data as a combination of several bell-shaped components, each capturing a possible subgroup or pattern. It uses soft clustering, meaning each data point receives probabilities of belonging to different components rather than being assigned to just one. This is useful when groups overlap, such as in customer, medical, or financial data, where clear boundaries may not exist. A Gaussian mixture model represents data as several components, each with an estimated size, center, and spread. The size shows how common the component is, the center gives its typical values, and the spread describes variation and relationships among variables. This makes the model useful for clustering, estimating where data points are likely to occur, and detecting outliers. When fitting a Gaussian mixture model, choosing the right number of components is essential. Too few can hide meaningful patterns, while too many can fit random noise and create misleading clusters. A good fit balances statistical estimation with careful interpretation, using the model to describe uncertainty and variation rather than treating groups as fixed categories. Python code, GMM fitting. Fit a Gaussian mixture model to synthetic clusters to identify the underlying components. Use soft membership probabilities to show how overlapping points can belong partly to multiple clusters, and visualize the learned components along with the uncertain boundaries between them. We import key Python libraries for generating, visualizing, and clustering data. NumPy supports numerical array operations, Matplotlib creates plots, and Scikit-Learn provides machine learning tools. From Scikit-Learn, we use a synthetic data generator and a Gaussian mixture model to cluster data with overlapping components. We define two-dimensional cluster centers, then use Scikit-Learn's makeBlobs function to generate 450 synthetic data points around them. The cluster spread is controlled by a standard deviation of 1.05, and a fixed random state makes the results reproducible. This produces both the data points and their true labels for use in soft clustering. Before fitting the Gaussian mixture model, the code verifies that the data has 450 rows and 2 columns, meaning each sample has 2 features. If the shape is incorrect, it raises an error to stop the process. This check helps ensure the data is properly structured and prevents problems during model fitting. We create a Gaussian mixture model with 3 components, assuming the data comes from 3 overlapping bell-shaped distributions. Using full covariance lets each component model its own spread and orientation, while a fixed random state makes the results reproducible. Fitting the model estimates the components' means, covariances, and weights, so the mixture best matches the observed data. A Gaussian mixture model can assign each data point to its most likely cluster, producing hard labels. It can also estimate soft membership probabilities, which show how likely each point is to belong to each cluster. These probabilities help reveal uncertainty, especially for points near cluster boundaries. For each data point, we look at its highest membership probability across the Gaussian mixture components to measure how confidently it belongs to a cluster. The point with the lowest of these maximum probabilities is the most uncertain assignment. We then identify that point's coordinates and review its probabilities for each component. The code reports the Scikit-Learn version, then summarizes the Gaussian mixture model by showing the rounded component weights. It also finds the data point with the most uncertain cluster membership, prints its rounded coordinates, and shows its rounded probabilities for belonging to each cluster. A new matplotlib figure and axis are created to set up the plotting area. The data is then shown as a scatter plot using the first two features for each point's position. Points are colored by their predicted labels with the Viridis color map, and slight transparency helps make overlapping clusters easier to see. The visualization shows how a Gaussian mixture model fits the data. Red X's mark the centers of the Gaussian components, while a black star highlights the point whose component membership is most uncertain. The plot is titled and labeled by the two feature dimensions, with a legend identifying components 0, 1, and 2, making it easier to assess the model fit and the distribution of points. This script fits a Gaussian mixture model with 3 components to synthetic two-dimensional data containing 3 overlapping clusters. After training, the model assigns each point a cluster label and a set of membership probabilities, showing both the predicted grouping and the uncertainty of each assignment. The visualization colors points by predicted cluster, marks the learned centers, and highlights the point with the most uncertain membership. It also reports the Scikit-Learn version, component weights, and the uncertain points probabilities to help assess how well the model captures the data structure. Covariance structures. In a Gaussian mixture model, each cluster is described not only by its center, but also by its covariance, which captures the cluster's shape, spread, and orientation. This matters because real data can form elongated, tilted, or uneven patterns. By modeling covariance, each Gaussian component can better represent relationships within the data and more accurately estimate which cluster an observation belongs to. In Gaussian mixture models, the covariance structure controls how flexibly each cluster can vary in shape and relationships between variables. More flexibility can capture complex, different clusters, while stronger restrictions can improve stability and reduce overfitting, especially with smaller datasets. The goal is to choose a level of flexibility that represents the data well, without fitting noise. Covariance structures in Gaussian mixture models control how each component spreads probability around its center. Wide covariances make a component cover more varied data, while narrow covariances keep probability close to the center. This affects how the model represents overlapping groups, unusual observations, and confidence in assigning data to components. In Bayesian models, prior assumptions can also guide covariance estimates and make them more stable. Python code. Covariance structures. This example compares covariance choices in Gaussian mixture models. Covariance determines the shape and orientation of each component, which changes how the model forms soft clustering boundaries. This setup imports the main tools needed for generating and modeling data. NumPy supports numerical work with arrays, Matplotlib creates visualizations, and the Scikit-Learn version helps with compatibility checks. Scikit-Learn is also used to create synthetic blob data and to fit Gaussian mixture models for modeling complex data distributions. We generate synthetic data with Scikit-Learn's MakeBlobs function, creating 500 points grouped into 2 clusters. Each cluster has a standard deviation of 1, and a fixed random seed of 42 makes the results reproducible. This data provides a controlled starting point for later Gaussian mixture model analysis. To create correlated features, we apply a transformation matrix to the data points. This stretches and rotates the original clusters, changing their shape and introducing relationships between features. The result is data that better represents more complex structures. Before modeling, the code verifies that the dataset contains 500 rows and 2 features, which is the expected structure for the Gaussian mixture model. If the data has a different shape, it raises an error to stop the process. This check helps prevent fitting problems by confirming the data is properly prepared. We create a Gaussian mixture model with two components, each using a full covariance matrix, so it can have its own shape and orientation in the data space. A fixed random state ensures the results are reproducible. The model is then fitted to the point dataset to learn parameters that capture the data's underlying structure. A Gaussian mixture model is created with two spherical components, meaning each cluster is assumed to have equal variance in every direction. A fixed random state makes the results reproducible, and fitting the model lets it learn the parameters that best describe the data under this assumption. We compare full and spherical covariance models on the points dataset using the Bayesian information criterion, or BIC. BIC balances model fit against complexity, and lower values indicate a better choice. After reporting the Scikit-Learn version, we print both BIC scores to one decimal place to see which model fits the data more effectively. The flexible Gaussian mixture model assigns each data point a set of soft probabilities across components. For each point, the largest probability is treated as the model's confidence in its assignment. Averaging these highest probabilities gives an overall confidence score. To visualize the model's soft decision boundary, we create a grid that spans the feature space. For each of the two features, we find the minimum and maximum values across the data and add extra padding on both ends. This gives the grid enough margin to cover all points clearly and show the boundary effectively. A grid of points is created across the feature space, covering the range of the data. The grid points are converted into pairs of feature values, and a full covariance Gaussian mixture model estimates each point's probability of belonging to the first component. These probabilities are then reshaped to match the grid, making it possible to visualize the model's soft decision boundary. Create a plotting canvas with a 7 by 5 inch figure. Then draw the data points as a scatter plot. The point positions come from the first two columns of the data array, while their colors show confidence values, meaning the highest membership probability for each point. A Viridis color scale and moderately sized markers make the confidence levels easier to see. A contour line is added to show where the two Gaussian components are equally likely, marking the soft clustering boundary. The plot is titled to identify it as the boundary for a full covariance Gaussian mixture model, and the axes are labeled as Feature 1 and Feature 2 for clarity. A color bar is added to show the membership confidence values for the scatter plot. It represents the highest component probability for each point, and the plot is then displayed on screen using Matplotlib's show function. This script shows how covariance assumptions affect Gaussian mixture models on two elongated correlated clusters. It compares a full covariance model with a spherical model using the Bayesian information criterion, where the lower score indicates the better fit, and also reports the full model's average membership confidence. A contour visualization of the full model shows soft cluster membership and the boundary where the two components are equally likely, illustrating that full covariance can capture the data's shape more flexibly than a spherical model. EM intuition. Expectation maximization helps fit a Gaussian mixture model when each observation's group membership is unknown. Instead of assigning each data point to one cluster, it treats membership as uncertain and gives each Gaussian component a responsibility based on how well it explains the observation. These soft assignments let the model represent the overall data distribution as a mixture of simpler patterns. The algorithm repeats two phases, expectation and maximization. First, It estimates how strongly each observation belongs to each component using the current parameters. Then, it updates the component means and covariances based on those weights. Repeating these steps gradually improves the model until the changes become small. Expectation maximization handles hidden labels by using responsibilities, or weighted evidence, to estimate model components such as Gaussians. It alternates between assigning provisional weights and updating the model, helping uncover hidden structure in uncertain data. Because results depend on the starting point, especially with overlapping clusters or many components, practitioners often run it several times and compare the outcomes. Mixture model selection, AIC-BIC. Scikit and Bayesian information criteria help choose the right complexity for a Gaussian mixture model. They compare how well a model fits the data while penalizing unnecessary parameters, which helps prevent overfitting. This makes them useful for selecting models with an appropriate number of components and covariance structure, favoring solutions that are accurate but still simple. AIC and BIC help compare models by balancing fit against complexity. AIC is more flexible and often favors models with stronger predictive detail, while BIC penalizes complexity more heavily and tends to choose simpler models. Use AIC when prediction is the priority, and BIC when simplicity and clearer explanation matter more. When choosing mixture models with AIC or BIC, compare both the number of components and the covariance structure. Spherical, diagonal, and full covariance models offer increasing flexibility, from round clusters to more complex correlated patterns, but added flexibility can increase overfitting risk. AIC and BIC help weigh better fit against greater complexity, and the final choice should also consider visual checks and domain knowledge. Python code, AIC, BIC. Use AIC and BIC to compare mixture models and choose among candidates. Different covariance choices affect model complexity penalties, and the preferred model is the one with the lower criterion value. This setup imports the main Python tools needed for a clustering workflow. NumPy and Pandas support numerical and tabular data handling, while Matplotlib is used for visualization. Scikit-Learn provides tools to generate synthetic blob data and fit a Gaussian mixture model, which is commonly used for clustering and density estimation. We create a synthetic two-dimensional dataset with 3 cluster centers at -3, -1, 0, 2, and 3, -1. Using Scikit-Learn's blob generator, we produce 450 samples spread around these centers with a standard deviation of 0.9. A fixed random seed makes the results reproducible, and the slight overlap between clusters makes the data useful for testing mixture models. We transform the data by multiplying it with a small stretch matrix, which changes its shape by scaling and skewing it. This makes the data structure easier for models with full covariance to capture. As a result, a Gaussian mixture model may fit the transformed data more effectively. Before modeling, the code verifies that the dataset has 450 rows and 2 features. If the dimensions are wrong, it raises an error to signal that the data was not generated as expected. This quick validation helps prevent problems later in the analysis. The process compares several Gaussian mixture model settings by testing spherical, diagonal, and full covariance structures with 1 to 5 components. Each model is fit to the data using a fixed random state and multiple initializations for reliability. After fitting, the Scikit and Bayesian information criteria are recorded to evaluate model quality while penalizing unnecessary complexity. The results are organized into a Pandas data frame with the covariance type, number of components, and AIC and BIC scores. The AIC and BIC values are rounded for easier comparison. Then the models with the lowest AIC and lowest BIC are selected. This quickly identifies the best performing models under each criterion. The code first reports the Scikit-Learn version to support reproducibility. It then prints the best Gaussian mixture models chosen by AIC and BIC, including each model's covariance type and number of components. Finally, it ranks all results by BIC and displays the top 5 models as a quick summary of the strongest candidates. The plot compares BIC values across different numbers of components for spherical, diagonal, and full covariance types. For each covariance type, the matching results are selected and plotted as a separate labeled line with markers. This makes it easy to see how model fit changes with both the number of components and the covariance structure. The plot is formatted to compare Bayesian information criterion values for different Gaussian mixture model candidates. It shows the number of mixture components on the horizontal axis and the BIC score on the vertical axis, where lower values indicate a better model. A legend distinguishes the covariance types, and the plot is then displayed for visual comparison. This script compares Gaussian mixture models using the Scikit and Bayesian information criteria to choose a good fit for synthetic clustered data. It tests different numbers of components and covariance types, then scores each model with both criteria. The lowest scores identify the preferred models, and the results highlight how model selection balances better data fit against added complexity. Bayesian mixtures. Bayesian mixtures handle uncertainty about how many clusters a mixture model should have by treating model parameters as uncertain and guided by prior distributions. Instead of choosing among fixed models using criteria like AIC or BIC, they combine prior beliefs with evidence from the data to assess possible component structures. This is useful for soft clustering, where points can belong to groups with different probabilities, and it helps avoid creating clusters that the data does not support. Bayesian mixtures reduce overfitting by placing probability distributions on model parameters, such as means and covariances. This regularizes the model, discouraging extreme or overly complex solutions unless the data clearly supports them. As a result, they help analysts find patterns that balance useful detail with reliable generalization. Bayesian mixture models help choose covariance structures by balancing flexibility, stability, and interpretability. Flexible covariance matrices can describe complex clusters with fewer components, but may be unstable with limited data, while constrained covariances are easier to estimate, but may require more components. By combining prior information, uncertainty, and criteria such as AIC and BIC, these models support choices that fit the data while still representing the underlying process clearly. Python code, Bayesian mixtures. Compare mixture complexity with Bayesian regularization by looking at how covariance choices influence the number of selected components. The printed scores help identify when the data supports a simpler mixture structure. We import NumPy for numerical work and array handling, then use Scikit-Learn for machine learning tools. From Scikit-Learn, we bring in the make_blobs function to create synthetic clustering data, along with Gaussian mixture and Bayesian Gaussian mixture models. These models fit data as mixtures of Gaussian distributions, with the Bayesian version helping choose the number of components automatically through regularization. We generate synthetic data with Scikit-Learn's make_blobs function, creating 450 samples with 2 features. The data is arranged around 3 cluster centers, with different spreads for each cluster. A fixed random state ensures the same dataset is produced each time, and the function returns both the feature values and the true cluster labels. Before modeling, The code verifies that the generated features have 450 rows and 2 columns. If the data has a different shape, it raises an error to signal an unexpected format. This quick validation helps catch structural problems early and prevents issues later in the analysis. The code uses NumPy's finite value check to make sure every feature value is valid, with no infinity or not a number entries. If any invalid values are found, it raises an error stating that all features must be finite. This helps prevent failures or incorrect results during model fitting. We prepare to compare Gaussian mixture models with 1 to 6 components, representing different levels of model complexity. To choose the best option, we track the lowest Bayesian information criterion score and the matching number of components. This helps identify the model that best balances fit with simplicity. To choose the best number of components for a Gaussian mixture model, we test several possible counts. For each one, we fit a model to the feature data and calculate its Bayesian information criterion, or BIC, which balances model fit with complexity. We keep the component count with the lowest BIC, giving us the preferred model size based on this criterion. We configure a Bayesian Gaussian mixture model with up to 6 components, using full covariance so each component can have its own covariance structure. A Dirichlet process prior with a small concentration value encourages sparse component weights, helping the model ignore unnecessary components. The model is allowed enough iterations to converge, and a fixed random state makes the results reproducible. A Bayesian Gaussian mixture model is fitted to the feature data to estimate its mixture parameters. After fitting, the component weights are checked to see which parts of the mixture matter most. Any component with a weight greater than 0.05 is treated as active. And counting these active weights gives the number of components that significantly contribute to the model. The model's component weights are rounded to make their importance easier to see, and the Scikit-Learn version is noted for reproducibility. The results compare the best component count chosen by the Bayesian information criterion with the Bayesian model's active components, defined as those with weights above 0.05. The key takeaway is that a Bayesian mixture model can include extra components, but unsupported ones receive near zero weights, so the model effectively simplifies itself. This script shows how Bayesian regularization can make mixture models simpler. It compares standard Gaussian mixtures, chosen using the Bayesian information criterion, with a Bayesian Gaussian mixture that can start with more components than needed. The Bayesian model uses a Dirichlet process to give near zero weight to unsupported components, leaving only the active ones. The main point is that Bayesian mixtures can reveal a simpler cluster structure by automatically downweighting unnecessary components. Dirichlet priors. Dirichlet priors describe uncertainty about the component weights in a mixture model before seeing data. In Gaussian mixtures, these weights represent each component's share and must be non-negative and add up to 1, so the Dirichlet distribution fits naturally. A strong balanced prior encourages components to be used evenly, while a weak prior lets the data determine the weights. This helps control mixture complexity by influencing whether extra components remain active or fade out during fitting. The concentration of a Dirichlet prior helps control complexity in mixture models. High concentration keeps probability spread across many components, while low concentration favors a few dominant components and makes the rest negligible. This helps the model avoid unnecessary groups and reduce overfitting in applications such as segmentation, imaging, and monitoring. Dirichlet priors offer a Bayesian alternative to choosing mixture model complexity with criteria like AIC and BIC. Instead of testing many separate models, The Bayesian approach can begin with many components and let the prior and data determine which ones are useful. The prior choice still matters, especially with small or noisy data, but it makes assumptions explicit and can support flexible models without adding unnecessary complexity. This can improve clustering, density estimates, and decisions about the number of components. Python code, Dirichlet priors. This example compares different strengths of a Dirichlet prior in a mixture model. Sparse priors can push unnecessary component weights towards zero, effectively deactivating extra components. The learned weights show how the prior influences which components remain active. The script imports the main tools needed for a clustering example: NumPy for numerical array work, Matplotlib for plotting, and Scikit-Learn utilities to generate synthetic blob data and fit a Bayesian Gaussian mixture model. It also imports Scikit-Learn itself, so the script can later check the library version. We generate synthetic data with Scikit-Learn's MakeBlobs function to create 3 clear clusters for mixture modeling. The dataset contains 450 samples, with a moderate cluster spread and a fixed random state, so the results are reproducible. The function returns the data points and their true cluster labels, which can be used for validation but are not used to train the model. Before modeling, the code verifies that the generated data has 450 rows and 2 features. This confirms the data is in the right format for the mixture model. If the shape is wrong, it raises an error to stop the process and prevent later modeling problems. We fit 2 mixture models with more components than needed to see how different Dirichlet prior strengths affect the results. The prior values, 0.01 and 10.0, let us compare how strongly the model encourages or discourages active components. We also store the learned component weights from each model, so their effects can be compared. For each prior value, a Bayesian Gaussian mixture model is fitted to the generated features using 8 initial components, a fixed random state, and up to 500 iterations. After fitting, the model's learned weights are stored. Comparing these weights shows how the strength of the prior influences how many mixture components remain active. The process counts how many mixture components have meaningful weights in each model. For each learned set of weights, it checks how many are greater than 0.05 and records that number. These counts make it easier to compare how different prior strengths influence the number of active components in the mixture model. The code first reports the Scikit-Learn version to confirm the running environment. It then compares how many mixture components remain active under a sparse prior and a strong prior. This shows how prior strength affects model complexity by changing which components receive meaningful weight. We define possible mixture components numbered 1 through 8, then create a plotting area to visualize the learned weight of each component. This setup helps compare how different Dirichlet prior strengths influence the complexity of the mixture model. The plot compares learned mixture weights under 2 Dirichlet prior strengths, 0.01 and 10.0. Each set is shown with different markers and a legend, with component number on the x-axis and learned mixture weight on the y-axis. This visualization highlights how the strength of the Dirichlet prior influences mixture complexity. This script shows how Dirichlet prior strength controls the complexity of a Bayesian Gaussian mixture model. Using data with 3 clusters, it fits 2 models that start with 8 possible components, one with a very sparse prior and one with a strong prior. The sparse prior turns off more unused components, while the strong prior keeps more components active. By comparing the active component counts and learned weights, the example illustrates how priors influence the effective number of mixture components. Covariance models. Empirical shrinkage. Empirical shrinkage helps estimate covariance when the sample covariance matrix is unreliable, especially when there are many features but few observations. In such cases, noise can exaggerate correlations and distort relationships among variables, which can harm tasks like clustering or anomaly detection. Shrinkage reduces this instability by pulling the noisy estimate toward a simpler, more stable target, balancing the data with a reliable covariance model. Empirical shrinkage improves covariance estimates by adding a small bias to reduce instability. In Gaussian mixture models, this helps each component describe spread and dependence more reliably, especially when clusters have little data. By regularizing noisy correlations, shrinkage reduces overfitting and keeps cluster shapes based on meaningful patterns rather than random variation. Empirical shrinkage improves covariance analysis by balancing flexibility with stability. When data is abundant, estimates stay close to the observed covariance. When data is sparse or noisy, they shift toward a more reliable target. This helps reveal dependable patterns in areas such as genomics and environmental monitoring, supporting tasks like prediction and clustering without overfitting noise. Python code. Empirical shrinkage. This example compares empirical covariance estimates with shrinkage estimates. Shrinkage helps stabilize covariance estimates when there are few samples, leading to better conditioned results. We import NumPy for numerical work with arrays, Matplotlib PyPlot for creating plots, and Scikit-Learn for machine learning tools. From Scikit-Learn's covariance module, we use empirical covariance for a direct covariance estimate and Ledoit-Wolff for a shrinkage-based estimate that can be more stable with limited data. We set the NumPy random number generator with a seed of 42, so it produces the same random sequence each time the code runs. This makes results reproducible, which is important for simulations and experiments that need consistent outcomes. The setup uses 30 samples and 20 features, creating a high-dimensional case with relatively few observations. This makes covariance estimation less stable and more sensitive to data variation. It provides a useful setting for showing how shrinkage can help stabilize the covariance matrix. We create a synthetic dataset by first generating hidden factors with a random normal distribution, then using random loadings to turn those factors into observed features. Added random noise, scaled to control its effect, gives the data realistic variability. Together, these steps produce correlated features suitable for covariance estimation. The data matrix is created by combining latent factors with a loadings matrix, which builds correlations between features. Noise is then added to reflect real-world variability. Finally, each feature is centered by subtracting its mean, so covariance estimates reflect the data's spread rather than its average values. We verify that the data has the expected number of samples and features before analysis. If the shape is incorrect, an error is raised to signal that the data is not organized properly as samples by features. This check helps protect the accuracy of the covariance estimation process. We compare two ways to estimate covariance from the same data. The empirical covariance model uses the sample data directly, while the Ledoit-Wolff shrinkage model adjusts the estimate to make it more stable, especially when there are few samples relative to the number of features. This lets us contrast the raw covariance estimate with a more regularized version. We compare the eigenvalues of the empirical covariance matrix and the shrinkage covariance matrix. These eigenvalues show how variance is spread across principal directions. By comparing them, we can see whether shrinkage makes the covariance estimate more stable. We assess covariance matrix stability by comparing their condition numbers. Using NumPy's linear algebra tools, We compute this value for both the empirical covariance matrix and the shrinkage covariance matrix. A lower condition number means the matrix is less sensitive to small input changes, so the comparison shows whether shrinkage improves stability. The code reports key diagnostics for a Ledoit-Wolff covariance estimate. It shows the Scikit-Learn version for reproducibility, the shrinkage amount to indicate the level of regularization, and the condition numbers of both the empirical and shrinkage covariance matrices. Comparing these condition numbers demonstrates how shrinkage improves matrix conditioning. We create a plot to compare the eigenvalues of covariance matrices before and after shrinkage. The feature numbers form the horizontal axis, making it easier to see how shrinkage reduces extreme eigenvalues and produces a more moderated covariance structure. The plot compares covariance eigenvalues before and after shrinkage by showing empirical eigenvalues and shrinkage eigenvalues across their ranks. The axes indicate eigenvalue rank and covariance eigenvalue magnitude, and a legend distinguishes the two lines. This visualization makes it easy to see how shrinkage changes the eigenvalue structure of the covariance matrix. This script shows how shrinkage can make covariance estimates more stable when there are more features than samples. It compares the empirical covariance with the Ledoit-Wolff shrinkage estimator on synthetic correlated data. The output reports the shrinkage amount and condition numbers, where lower values mean better stability. Shrinkage usually lowers the condition number and moderates extreme eigenvalues, producing a more balanced and reliable covariance estimate. Sparse precision. Sparse precision modeling estimates the inverse of a covariance matrix to reveal direct relationships between variables after accounting for all others. This is especially useful in high-dimensional data, where apparent correlations may come from indirect effects. By keeping only the strongest direct connections, it simplifies complex relationships, such as identifying directly linked stocks in finance or direct biomarker relationships in medicine. Sparse precision estimation is useful when there are more variables than observations, because ordinary covariance estimates can be unstable and difficult to interpret. Regularization favors simpler, more stable models, unless the data clearly support added complexity. The result is a conditional dependence graph that shows direct relationships after accounting for other variables, helping reveal direct links between brain regions or genes, even with limited samples. Sparse precision models support decision-making by emphasizing direct relationships, which makes risk models and anomaly detection easier to interpret. They can also stabilize covariance patterns in mixture models when data is limited, helping reveal conditional links in areas like customer behavior or manufacturing sensors. Their usefulness depends on choosing appropriate sample sizes and regularization strength, so sparsity must be balanced to avoid losing important signals or keeping noise. Python code. Sparse precision. This example shows how graphical lasso estimates sparse precision relationships, highlighting direct conditional associations between variables. It compares covariance patterns with precision patterns to show how these relationships differ. The script imports key tools for numerical analysis, visualization, and covariance modeling. NumPy handles array-based computations, Matplotlib creates plots, and Scikit-Learn provides the graphical lasso method for estimating sparse inverse covariance matrices. The full Scikit-Learn library is also imported so its version can be checked later. A random number generator is initialized with a seed of 42 to make the synthetic data reproducible. This ensures the same random values are produced each time the code runs, supporting consistent results, easier debugging, and fair comparisons. The data setup creates 180 samples, with 2 hidden factors drawn from a normal distribution to represent underlying influences. It also adds normally distributed noise across 5 variables, scaled to introduce realistic variation, so the variables are not perfectly tied to the factors. The code builds a dataset with variables that share hidden influences. It combines columns where 2 variables come from one hidden factor, 2 come from another, and 1 is pure noise. This creates indirect correlations that a model can later try to detect. The code first verifies that the dataset has 180 rows and 5 columns before any modeling begins. If the dimensions are different, it raises an error to signal the mismatch. This early check helps catch data problems before they affect later analysis. Centering the data means subtracting each column's mean from its values. This removes the influence of average levels, so covariance focuses on how the variables vary together and relate to one another. The code uses graphical lasso to estimate a sparse inverse covariance matrix, helping reveal direct conditional relationships between variables. It sets a sparsity control value and an iteration limit, then fits the model to centered data to learn the dataset's dependency structure. To compute partial correlations from a fitted graphical lasso model, start with its precision matrix, which is the inverse covariance matrix, and reflects conditional relationships between variables. Normalize the negative precision values using the square roots of the diagonal entries, so the results can be interpreted like correlations. Finally, set the diagonal values to 1, since each variable is perfectly correlated with itself. The code identifies meaningful conditional relationships by marking partial correlations whose absolute values are greater than 0.05. It then counts the non-zero links outside the diagonal, adjusts for the matrix's symmetry, and returns the estimated number of direct links between variables. The code reports the Scikit-Learn version to support compatibility and reproducibility, then summarizes the dataset by showing its number of variables and samples. It also prints the estimated number of direct links between variables, based on non-zero off-diagonal entries in the partial correlation matrix, giving a quick view of the model's inferred conditional dependencies. Create a matplotlib figure and axis to set up the plotting area. Then, display the partial correlation matrix as a color-coded image. The image uses a range from -1 to 1, with a cool to warm color scale, making it easier to see the strength and direction of relationships between variables. The plot visualizes sparse precision values as partial correlations between variables. Both axes are labeled by variable index, and a color bar shows the scale of the partial correlation values. Displaying the plot makes it easier to inspect the sparse precision relationships among the variables. This script uses synthetic data from 2 hidden factors to estimate direct relationships among 5 variables. After centering the data, it applies graphical lasso to produce a sparse inverse covariance matrix. Then it converts it into partial correlations for easier interpretation. It counts the non-zero direct links and displays the sparse pattern as a heat map, helping reveal conditional dependencies in the data. Robust covariance. Robust covariance estimation reduces the influence of unusual data points that can distort the ordinary sample covariance matrix. This helps reveal the main relationships among variables more accurately, especially in tasks like clustering and anomaly detection. By limiting the effect of outliers, such as rare events or errors, robust methods better capture the data's core structure. Robust covariance estimates the main shape of data without letting outliers distort the result. Unlike traditional covariance, it reduces the influence of extreme or unreliable points and focuses on the core pattern. This is important for multivariate distance calculations, which depend on both variable scales and correlations. In areas such as quality control and environmental monitoring, it helps separate true anomalies from typical behavior more reliably. Robust covariance estimation helps reveal reliable data structure, even when outliers or contamination are present. Its inverse, the precision estimate, supports analysis of conditional relationships, outlier scoring, and clustering. Rather than ignoring extreme points, robust methods limit their influence, which is especially important in mixture modeling and soft clustering, where outliers can distort components or create false groups. This makes the results more dependable in areas such as finance and healthcare, where meaningful variation and extreme observations often occur together. Python code, robust covariance. This example contrasts ordinary covariance with robust covariance. Outliers can distort covariance-based distance estimates, while robust covariance gives a better description of the main data cloud. We import NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning tools. From Scikit-Learn, we use two covariance estimators: empirical covariance for a standard estimate, and minimum covariance determinant for a more robust estimate that is less affected by outliers. A fixed random seed of 42 is used, so the results can be reproduced. Then, 120 two-dimensional data points are generated from a multivariate normal distribution centered at the origin, with a covariance structure that creates correlation between the two dimensions. We add a small set of extreme data points, called outliers, to the main data cloud. These points are combined into one dataset, so we can study how unusual observations influence different covariance estimates. Before fitting the covariance estimators, the code verifies that the dataset has 124 rows and 2 columns. If the shape is different, it raises an error to signal the mismatch. This check helps ensure the data is properly structured and prevents problems during fitting. We compare two ways to estimate covariance in data with possible outliers. The empirical covariance method treats all points equally, so it can be strongly influenced by unusual values. The minimum covariance determinant method is more robust and less sensitive to outliers. A fixed random state ensures the results can be reproduced. We compare Mahalanobis distances computed with ordinary and robust covariance estimates. The ordinary covariance reflects the overall data shape, but can be affected by outliers, while the robust estimate reduces their influence. By averaging the distances for the last 4 points, which are the outliers, under both methods, we can see how differently each approach judges their distance from the data center. The process checks the Scikit-Learn version for reproducibility, then compares ordinary and robust covariance estimates. It prints each covariance determinant to show the estimated spread of the data, with the robust estimate being less affected by outliers. It also compares the average Mahalanobis distance of the outliers under both estimates, showing how the robust covariance better represents the main data cloud. To draw covariance ellipses, start by generating points around a full circle using angles from 0 to 2 pi. The cosine and sine of these angles form a unit circle, which can then be transformed by the covariance matrix into an ellipse that shows the data's two-dimensional spread. The covariance ellipse function turns a covariance matrix into an ellipse showing 2 standard deviations around a center point. It finds the matrix's eigenvalues and eigenvectors, uses the eigenvalues to set the ellipse's radii, and then scales and rotates a circle using the eigenvectors. The result is an ellipse positioned at the center that reflects the covariance structure. We create 2 covariance ellipses to compare how the data spread is estimated. The ordinary ellipse uses the classical location and covariance estimates, while the robust ellipse uses robust estimates that are less affected by outliers. This makes the robust ellipse a better summary of the main data cloud when outliers are present. Create a matplotlib figure and axis, then use a scatter plot to show two groups of points. The main data cloud is plotted with smaller markers, while the outliers are plotted with larger markers and a separate label. This makes it easier to compare the distribution of the main data with the outliers. The code plots two covariance ellipses to compare ordinary and robust covariance. Each ellipse is drawn and labeled, and the plot title emphasizes that robust covariance is less affected by a few extreme points. The horizontal axis is labeled as feature 1 to identify the first data feature. The plot is finalized by labeling the vertical axis as feature 2, adding a legend to identify the data groups and covariance ellipses, and setting an equal aspect ratio so distances are represented accurately on both axes. The visualization is then displayed for analysis using matplotlib's show function. This example compares ordinary covariance estimation with a robust approach when outliers are present. A two-dimensional data cloud is created with a few extreme points. Then covariance is estimated using both the empirical method and the minimum covariance determinant method. The robust estimate is less affected by the outliers, producing a tighter ellipse around the main data cloud and better preserving its underlying structure. In this lecture, you learned to fit Gaussian and Bayesian Gaussian mixture models for soft clustering and density modeling. Select mixture complexity using covariance structures, AIC and BIC, and apply covariance and precision estimators for robust or structured covariance analysis. In the next lecture, Lecture B, we will go over density anomalies.
Thank you for your attention. See you all in the next lecture.